Imagine a machine so powerful it could break every code on Earth, yet so mysterious that it doesn't think in ones and zeros, but in infinite possibilities all at once. A machine that doesn't just calculate, it imagines. This isn't science fiction. This isn't the future. It's happening now, in the quiet hum of laboratories across the planet, where physicists and dreamers are rewriting the rules of computation itself. In this world, data doesn't move through circuits, it ripples through reality. This is the dawn of quantum computing, a technology so strange it defies everything we thought we knew about logic, cause, and effect, where a bit can be both 1 and 0, true and false, light and dark all at the same time. In this new frontier, certainty collapses, and possibility becomes power. Welcome to the story of how humanity learned to think in quantum. For decades, our digital world has been built on the simplest foundation imaginable: binary code. Every photo, song, and heartbeat, recorded by machines, boils down to a long chain of ones and zeros. This has powered empires, sent humans to the moon, and built an internet that connects billions of minds. But nature doesn't think in binary. Beneath the surface, reality is painted with shades of probability. Quantum computing dares to mimic that chaos. It doesn't use bits, but qubits, units that can exist as both 0 and 1 at the same time. Imagine flipping a coin and, while it spins, it's both heads and tails. Only when it lands does it decide. That's how qubits behave. In superposition, it's as if the universe itself whispers, "Why choose one when you can be both?" And in that paradox lies the next revolution. Not faster machines, but a whole new way of thinking. The deeper we dive into the quantum world, the stranger it becomes. Down there, reality doesn't follow the clean logic of cause and effect. It dances. An electron can be in two places at once. A photon can behave as both a wave and a particle. Observation changes existence. It's unsettling, almost poetic. For centuries, scientists tried to cage this chaos with equations, yet every discovery led to deeper mystery. Quantum mechanics revealed that nature is not a machine. It's a story of probabilities. And quantum computing, it's our attempt to make that story readable, to use uncertainty as a tool, not a flaw. Through superposition and entanglement, we can link particles across space and time, so deeply connected that changing one instantly alters another. Einstein called it spooky action at a distance. Today, that spooky action might just become the foundation of the most powerful computers ever built. So, what exactly is a qubit made of? It could be a single trapped ion, suspended by lasers in perfect stillness, or a tiny loop of superconducting current, chilled to near absolute zero. Some qubits live in photons, others in the spin of electrons. Each is a fragile pocket of potential, a momentary glimpse of infinite possibilities. But there's a problem. The instant a qubit interacts with the world, it loses its magic. This collapse, known as decoherence, turns quantum fluidity back into solid yes-or-no reality. To fight it, engineers isolate qubits from heat, noise, even light itself, keeping them colder than outer space. Every qubit that survives becomes a miracle of precision, a whisper balanced on the edge of existence. Quantum computers aren't just machines, they're sanctuaries for uncertainty, and every calculation is a negotiation with the laws of nature themselves. In a classical computer, problems are solved one step at a time, like a person turning over cards in a deck. But a quantum computer can look at every card simultaneously. This is called quantum parallelism, and it changes everything. 10 qubits can represent over 1,000 states at once. 50 qubits, more than the number of atoms on Earth. It's not linear, it's exponential. While a normal computer follows one path, a quantum computer explores all paths, then collapses into the right answer when measured. This means problems once thought impossible, like simulating molecules or cracking vast codes, might take minutes instead of millennia. It's power beyond speed. It's depth beyond comprehension. When you watch a quantum processor run, it's like watching possibility itself being distilled into truth. Billions of potential realities collapsing into one elegant solution. In 2019, Google announced a milestone that rippled through the world: quantum supremacy. Using a 53-qubit processor called Sycamore, their machine performed a calculation that would have taken the world's fastest supercomputer over 10,000 years in just 200 seconds. For some, it was a publicity stunt. For others, it was history, because in that brief moment, humanity crossed the threshold. For the first time, a human-made device operated on principles not bound by classical logic. The task itself, random number generation, wasn't useful, but the meaning was profound. Proof that the impossible could be done. The scientists who watched those results appear on screen described it not as victory, but as awe. They weren't looking at code. They were looking at the fabric of the universe being used as a processor. The line between human invention and natural law had just blurred forever. Now, imagine what happens when this power becomes practical. A world where quantum computers design new medicines by simulating molecules with perfect accuracy, where they discover superconductors that make energy loss obsolete, where global supply chains, traffic networks, and climate systems are optimized in real time. The possibilities ripple outward like waves in a still pond. Quantum algorithms could crack the mysteries of protein folding, a puzzle nature itself seems to guard. They could predict financial crashes, model the human brain, or unlock secrets of the cosmos. It's not just computation, it's creation, the ability to shape outcomes by understanding the deepest patterns of existence. Yet, as always, power this great comes with a warning, because in the quantum world, light and shadow grow together. And if we can build the ultimate problem solver, we must also face the problems it could unleash. Every secret you've ever sent, every password, every message, every financial record is protected by encryption. These codes rely on the fact that some problems are simply too hard for classical computers to solve in any reasonable time. But a powerful enough quantum computer could solve them almost instantly. The cryptography that guards our world could crumble like sand. Banks, governments, defense systems, all vulnerable. Bitcoin's blockchain, thought to be unbreakable, could vanish in a puff of quantum logic. It sounds like a thriller, but it's a real concern, and it's why scientists are already developing quantum-safe encryption. The same technology that might cure cancer could also collapse the digital foundations of civilization, and that is the paradox of human progress. Every tool that saves us carries the potential to undo us. The question isn't whether quantum computers will change the world, but how we'll handle the change. Behind closed doors, a new kind of arms race has begun. Not for missiles, not for land, but for qubits. The US, China, and the European Union pour billions into secret projects, while companies like IBM, Microsoft, and Google race to be first. Quantum supremacy isn't just a scientific achievement, it's a strategic weapon. Whoever masters quantum first gains control over communication, defense, and information itself. A country with quantum advantage could decrypt global networks or design materials that shift the balance of power. The stakes are invisible, yet immense. And unlike nuclear arms, quantum weapons leave no mushroom cloud, only silence. The competition drives innovation at an astonishing pace, but also fear, because power this subtle, this immense, is not easily shared. The question lingers in every lab and boardroom. What happens when one nation controls reality's code? For all its promise, quantum computing remains fragile, heartbreakingly so. Qubits are sensitive beyond imagination. A whisper of heat, a flicker of light, even a single vibration can destroy their state. Entire calculations can collapse in a fraction of a second. This is why quantum machines live in carefully controlled chambers, colder than outer space, shielded from interference. To scale them up, we need stability, and to achieve that, scientists are inventing something extraordinary. Quantum error correction. Imagine hundreds of qubits working together to protect a single piece of information, weaving a fabric of entanglement so dense that no single failure can tear it. It's computational teamwork at the edge of chaos. We're not there yet, but progress is accelerating. Each breakthrough, each extra qubit, brings us closer to the moment when quantum computers become not just possible, but practical. In laboratories around the world, researchers are using small-scale quantum computers to model the unimaginable. At IBM, they're simulating the behavior of complex molecules to design new drugs. At Google, they're testing optimization algorithms for energy grids. At MIT, students are exploring ways to make AI itself quantum. The results are early, but breathtaking. Quantum computing has already solved chemistry problems that classical supercomputers couldn't even begin. It's predicting molecular interactions, designing catalysts, and optimizing logistics routes that could save millions of tons of carbon emissions. It's as if we've built a lens powerful enough to peer into nature's code. And finally, we can read it. This isn't just about faster computing, it's about understanding. Each experiment brings us closer to a world where we can collaborate with the universe, not just compute within it. But pause for a moment. Why are we doing this? Why chase something so complex, so unpredictable, that even the people building it admit they barely understand it. Perhaps it's because this is who we are, creatures of curiosity, born to reach beyond the known, from fire to flight, from the atom to artificial intelligence. Every leap we've made began with a question that seemed absurd. Quantum computing is no different. It's not just an invention, it's a mirror. It reflects our endless hunger for meaning, our refusal to accept limits. The more we learn about the universe, the more it teaches us humility. Every qubit, every shimmering particle of potential, reminds us that certainty is an illusion, and that beauty often lies in the unknown. Maybe that's what draws us to it. Maybe, in mastering uncertainty, we're really trying to understand ourselves. Perhaps the most haunting truth of all is this: we, too, are quantum. We exist in superposition between who we are and who we might become, between fear and faith, between logic and love. Quantum computing, at its core, teaches us that opposites can coexist, that being uncertain doesn't mean being lost, it means being alive. Superposition isn't chaos. It's potential waiting to be observed. Every human choice is a kind of quantum collapse. We become what we decide to see. So, maybe this technology isn't just about harnessing particles. Maybe it's about understanding the human spirit, the courage to embrace both doubt and hope, to live within the tension of both, and instead of either or. The universe itself thrives in paradox, and perhaps, by learning from it, so can we. In the years to come, quantum computing could transform everything, from artificial intelligence to climate science, from economics to art. We may one day simulate consciousness itself, not as lines of code, but as quantum waves of possibility. Our machines could help us glimpse the nature of thought, of emotion, of the soul, and maybe that's where all this leads, not to domination, but to deeper connection. The quantum age won't be defined by speed or power, but by understanding, a merging of logic with mystery, of computation with creativity. Perhaps one day, quantum computers will teach us not just how the universe works, but why it exists at all. And in that moment, we might realize the greatest computer ever built was the cosmos itself, and we are simply learning to speak its language. So, as you finish this story, look around. Every atom in your body, every flicker of thought, every breath, it's all quantum. Beneath the surface of your existence, particles are weaving a symphony of uncertainty, collapsing into reality each time you choose, each time you act. You are a living quantum system, infinite possibilities condensed into a single moment of being. Maybe that's the true meaning of this technology, not to build something outside us, but to awaken what's already within. We are not binary creatures of zeros and ones. We are waves, fluid, infinite, ever, and like the qubits we've created, we exist in the space between both fragile and eternal. The future isn't coming. It's already here, humming quietly beneath the surface of everything. And if we listen closely, we can hear it whisper back. We are quantum,